All right, everybody, our last video on the Pythagorean Theorem for Unit 2 is dealing with the advanced application questions. Now, advanced application, do not make them harder. They're just different. So within the advanced applications, what we're going to be doing is using the application pieces that we did before, which was to identify missing side lengths in right triangles. We needed the concept and the formula for that. We're not going to be classifying triangles in this case. However, it doesn't mean that you can't sometimes have the two of these blend together. But in this video, we're going to limit ourselves to the formula and the finding of missing side lengths in problems that might hide that question a little better than they have up to this point. So to do that, I'm going to go ahead and get myself a nice clean paper. And let's check out one of the two most popular types. The first popular type is a problem that deals with distance. But the distance can be, well, two different types of distances. The distances could be what I'll refer to as real-world distances. And there's a variety of these. These could be a couple normal examples. A sports field, a basketball court, a football field, a soccer field, whatever. And for some reason, somebody will either measure or walk or be told to run a diagonal distance. And when I envision a rectangular field or court and a diagonal going from one corner to the other, I immediately envision what you could probably envision. I envision a right triangle. This is A, this is B, and this is C. And I could find, if I know two of them, I could find any other side. So in a soccer field, for example, it would be common to know the width and the length of the field. Same thing with football, same thing with basketball. And we could pretty easily use the a squared plus b squared equals c squared formula to find the missing diagonal. In another real world scenario, there's a lot of these kinds of questions. There's a building with a ladder leaning up against it. You're going to see my building and my ladder aren't very exciting as far as a sketch goes, but the building and the ladder are both on the ground, and not surprisingly, the building and the ground meet at 90 degrees. So here we go. We have ourselves the ladder leaning up against the wall. This would be the ladder over here. We have the distance from the bottom of the ladder to the base of the wall, and we have the distance from the base of the wall to the top of the ladder. So you might have any variety of things here. Maybe the ladder is 14 feet long, and the ladder reaches 10 feet up the wall. How far from the bottom of the ladder is the bottom of the wall, right? This is just Pythagorean theorem. The hypotenuse is, in this case, C. This one you could probably call A and B, or A and B, it doesn't really matter. And you could put those numbers in, find your Pythagorean theorem, and find the missing side length. As far as real world goes, we have, I guess in the same sketch, it could be somebody climbs up a ladder this time and goes down a water slide. This time the ladder would be kind of up and down, which would be a little dangerous, but you can get the idea, right? They go up a ladder and then they slide down a slide, and when they're done, they walk back to the base of the ladder to do it again. Once again, the real world problems are fairly straightforward. When you read them, you should remind yourself that in most cases, they're based off of a right triangle idea or a rectangle that has a diagonal cut through it. So we're not even going to really do those right here. There are lots of those in the notes. There's lots of those in Get More Math. There's lots of those in the examples. They're not really worth our time right now because they are so straightforward. The ones that this video is really for would be the ones that are going to be on a coordinate plane. And there are lots of different ways to do distances in the coordinate plane. If you're a parent watching this, or you're trying to help somebody out watching this video, you might remember that there's actually this whole long formula with the big square root symbol and stuff on the inside called the distance formula. That distance formula is really just the Pythagorean theorem kind of broken out. So what we're going to do is we're just going to show a very straightforward question that you would see relating distance, the coordinate plane, and the Pythagorean theorem. So here would be a sample question. Find the distance between the point 0, 0 and the point, let's say, 3, 5. All right, so you just want to know how long a line is that goes from the origin to point 3, 5. Now, we could create a distance formula out of this, but for most of us, we would probably rather just get a visual. So 0, 0 is where the two lines cross, the x and the y-axis. 3, 5, if I estimate this, is 3 to the right and 1, 2, 3, 4, 5 spaces up. So we're looking for that distance right there. And I have to admit, I hope you already see it. I'll switch colors. I hope you see that we just formed a right triangle with a missing side of C. So we're trying to find our hypotenuse. And how long is this side? Well, it was 3 spaces to the right. So 1, 2, 3. So this is a 3. And it was 5 spaces up. 1, 2, 3, 4, 5. So all I really had to do was make a little sketch. It doesn't even have to be on graph paper, and it doesn't even have to be all that accurate. Definitely not to scale, but now we have the A, we have the B, and we have the C. So just, again, kind of like we did here, just apply your Pythagorean theorem. And because I want to show you the example, so A squared plus B squared equals C squared. We're calling A the shortest side, so 3 squared plus 5 squared is the unknown side squared. 3 squared is 9, 5 squared is 25, is C squared. I add those up, I get 34 is C squared. Now at this point, we'll go ahead and square root both sides, and it depends what you want. You could, and I'm gonna just make sure I'm still on video, I am. You could simplify this, all right, depending on what the question asks. To simplify, you would use a factor tree off of 34. You might realize that 34 only breaks down to 2 prime numbers, 2 and 17. And neither of those break down. So in the simplify answer, you would actually just leave it as the square root of 34 and you'd be done. But you might be asked to estimate. It's common to estimate to the tenths. If you're estimating to the hundredths, then sometimes that's either rounding or it's not a great estimate. It's a good exact answer, but it's not a very good estimate. So the square root of 34, let's see, that's between the square root of 25 and the square root of 36. So it's 5, and you might recall, hopefully you know what I'm doing here, subtracting these and saying 9 over subtracting these and getting 11. And 5 and 9 elevenths from past experience is probably going to be about a 5.8 or 5.9. And for the purposes of the video, I'm going to go ahead and guess 5.9. I hope I'm right. So I'm going to say that my estimate is about 5.9, or it is exactly the square root of 34. But in reality, that's all there is to it. So 2 different types of problems. There's the real world style where you have a sports field or some other variation. I could see TV screens. I could see computer monitors. I could see, turn it outside. It's a cell phone screen or a cell phone and a diagonal that connects 2 corners. Slides or ladders, and then distance questions, which are a little bit more mathy, but can still be made into a sketch. So with that in mind, don't be scared to make yourself a coordinate graph. Don't be scared to make some points, count out some sides, and turn it into a right triangle like I did in blue, and then just watch to see what they're asking. Are they asking you to simplify, where you use factor trees and simplifying radicals, or are you estimating, where we use our estimation skills and get ourselves a decimal? So good luck.